everyone who's here in the room that if you are going to ask a question, please use these microphones that are scattered throughout, and hold down where it says touch so the red light is on while you're asking the question, so that people who are watching on the web can hear the question as well as the answer. And we actually do get people who watch both live and after the fact on the web, so we'd like them to be able to hear everything. And then I also want to remind all of the students, both here at PSU and if you're watching somewhere else, to sign up for the TransNow Student Conference. It's going to be in November. So hopefully you've gotten an email about that. If you haven't, talk to Casey Nolan, who is our speaker today, quite coincidentally. Casey is in our Masters of Urban and Regional Planning program. He's also working with Rob Bertini in the ITS lab, and he's organizing the conference, the student conference this year. So I'm going to turn it over to him, who's going to speak today on some safety and speed issues.
Thank you, Jennifer. What do I need to do here to get my presentation up for whoever's our tech guys? Because this isn't it. This isn't my presentation. Ah, there we go. That's the one. Did you get it? That's all right. Total traffic accidents?
Yeah.
Okay.
For the last 5
Great.
delay, and these are the maintenance costs for
Great.
keeping the highway
Thanks.
closed. So.
Cool. Sorry about the delay. Well, good afternoon, and thank you all for coming to learn about what I've been studying here at Portland State. It's my pleasure to share with you the research that I've been a part of in the Intelligent Transportation Systems Laboratory. I've been working on two aspects of highway speed and safety research, and together they make up the examination of the impact of speed upon highway safety, an Oregon perspective. So the first project involves determining the critical locations of speed-related crashes. I will briefly describe this project, explaining the problem and the methodology we use to address that problem, and then I'll go into a second and related project called an evaluation of an advanced curve warning system. I was more of a fundamental researcher on that project, so I'll go in depth a little bit more about the history of the project, the problem, the methodology, as well as the results of that project. So determining where speed-related crashes are occurring is an important aspect of addressing highway safety. A 5-year summary of crashes in Oregon showed that speed was a factor in 15% of those crashes. And this was slightly higher when injuries were involved, and significantly higher at 41% when those crashes were fatal. In 2001, which is the year that this research has focused on so far, speed actually contributed to 27% of total crashes, as displayed here in this chart. This peak year of crashes is coincidental and actually means very little to our research. In fact, it points out that the importance of continuing the study, which I will address later. Perhaps even more importantly than speed's relationship to crashes is the fact that speed can be reduced with a variety of countermeasures. Effective countermeasures are based on site-specific characteristics, including speed limits, geometry, and road characteristics of the such. Other factors to consider, sorry about that, would be surface conditions, lighting, and controls. So, knowing that speed is a major factor in crashes, injuries, and fatalities, and that speed can be reduced through well-placed countermeasures, we come to the objectives of this study. The first objective is to improve the procedures used to identify where speed-related crashes are occurring. And the second objective is to develop a customized list of possible speed-related safety countermeasures for those identified locations. Such a list would be a valuable resource for the Oregon Department of Transportation, and other decision makers, as these authorities have both limited time and resources to allocate for highway safety. To conduct the research, we started out with the Oregon DOT's reported crash database for 2001. We used the database from 2001 simply because that's what was made available to us, and with the hope that once we could determine where critical speed-related crashes were occurring, we could add additional years of data to strengthen the analysis. So there were over 20,000 reported crashes in the study year, and for each crash there are more than 20 field variables to help define what type of crash was occurring and the environment in which that crash occurred. Environmental characteristics may include such features as light, weather, surface conditions, and under traffic characteristics you can define a crash by what type of traffic control was present or not present, as well as whether or not speed was a factor. You can also look at different injuries that were occurring and define it by fatalities, serious injuries, or not so serious injuries. And then you can also define types of crashes by the type of vehicle that was involved, the action of the driver that was involved in the collision, things like road geometry, and the type of collision, whether it was head-on or rear end. So as you can see, there are seemingly an infinite number of ways to define and divide crashes by their types. We also use the Department of Transportation's GIS shapefile for the state's highway network. And this shapefile uses what's called a linear reference system identifier with the highway mileposts to identify where speed-related crashes were occurring. So I'll expand on that more a bit momentarily. In order to make the database useful for our purposes, we had to aggregate it into 1-mile segments. In other words, the identified locations that we found are not problem spots, but problem 1-mile segments. And then after we aggregated the data, we calculated the rate of crashes per million vehicle miles traveled. This was a tedious step as the ADT traffic numbers are not readily available in 1-mile segments. However, it was important because we wanted a real representative figure for the crashes to be useful for our purposes. After we calculated the rate per million vehicle miles traveled, we categorized those rates into low, medium, and high to easily display critical segments. And then lastly, we used a technique called dynamic segmentation in GIS to connect the reported crash database to the highway network shapefile. Using the linear reference system and the milepost numbers, dynamic segmentation allows us to display where speed-related crashes are occurring on the highway system with respect to other crash variables that I mentioned. So let's take a look at what happened in 2001. In general, speed-related crashes attributed to 27% of the total crashes, and 1.2% of those crashes resulted in one or more fatalities. 36% of those fatalities were speed-related crashes. Then when we were looking at the data, we also discovered 2 other variables that were important for speed-related crashes. When the surface of the road is icy, and whenever the road geometry necessitated a curve, the rate of speed-related crashes increased. So that's to say that speed-related crashes are overrepresented on icy surface conditions and along curves. So this map is just it's the speed-related crashes map. It's just raw crash numbers aggregated into 1-mile segments. And it basically just shows you where speed crashes are occurring. You can see that they're mostly occurring in the Portland, Salem, and Eugene areas. A little bit more in Eugene, possibly because it's less congested, allows for higher speeds, which tend to lead to crashes. There's another cluster of crashes along I-84 in northeastern Oregon. This map should make sense to us. It's basically saying that speed crashes are occurring where there's more vehicle miles being traveled. Here we have the rates of speed-related crashes per million vehicle miles traveled. Now this is where we're getting into calculating the ADT, and it shows quite a different picture. As I mentioned earlier, we've divided the crash rates into 3 categories. We have our low, medium, and high. And the yellow corresponds with low crash frequency, the blue to medium, and the red is our high or critical locations. So if you're used to working with crash rates, these numbers may seem a little high, But this isn't necessarily true. Just keep in mind that we're working with the 1 mile segments, not a specific crash intersection or location. So that bumps up the numbers. And this, yeah, go on. Yes, Linda?
I wanted to ask you why this map was up along 84 going east.
Yep.
Are any of those redded areas connected to any town or any type of area that's...
Off the top of my head, I do not know.
Okay. I just know it gets really wet and slick and icy.
That's a problem area in a lot of the different ways that we looked at the data, and snow, weather was a huge factor there. It's very hilly. There's some curves there. But as far as towns, off the top of my head, I'm not sure which ones of those each correspond with. Yep.
Hi, Casey. I was just wondering, are the concentrations for specifically the high concentrations related to just 1 segment miles, or are they groups of 1 segment miles?
Those are all 1 segment miles. When it's a group of a 1 segment mile, it would actually be a larger, well, actually, the one up top, most northernmost one, east of Portland, is probably a 2 mile segment. It's a little bit longer. And so it's represented that way by size. But for the most part, I think the rest of those are all 1 mile segments. Yes?
So this map, like you get the red dots, it's 13 to 27 million crashes per million miles traveled. So on a highway that only gets, let's say, 1 million cars to go by, these dots might represent 1 crash?
Correct. Yep, and I'll address that a little bit. And the main thing is that this is sort of presenting a methodology. We wanted to figure out how we could best use databases to look at these, to try and solve these problems. And then once we had that figured out, we would add additional years' data to that. Yes?
Did you just float that 1 mile segment over the highways and look for a minimum number of accidents before you calculated the rate, and then take a traffic count at that location when you had a minimum number of collisions?
No, I'm not quite sure what your minimum number of crashes.
Well, for your dots, you need to have a number of accidents and a number, a volume of traffic to come up with the rate.
Right.
How did you choose where to calculate those?
The volume and the rates. Another researcher did almost all of that part of this aspect of the research as far as calculating the ADTs. We got the ADT, however it came to us in this file, and then he went through and divided them up into 1 mile segments. So I'm not too familiar with that aspect of the research. And then correlated the crashes after we aggregated the data, just matched them up and sort of put them on top of each other. Is that getting at it? Yeah. So basically, this map, you can see that the crash rates tend to be in the more rural locations. And none of the critical segments on this map are in heavily populated areas. This also makes sense as the rural areas allow for faster speeds and tend to have less police enforcement. So a map like this can be a fairly useful tool because each of these 10 segments can be studied more in depth fairly easily with site visits and looking more in-depth analysis of the types of crashes that are occurring at each location. And then after more analysis, you begin to be able to piece together that list of proper countermeasure implementation. Then after filtering the database down to speed-related crashes, we analyzed each of the other characteristics that I mentioned. And as I said, icy surface conditions and curves were identified as important factors. And this graph sort of represents how we determined that. So the blue represents speed-related crashes, and the pink bars represent all crashes on this graph. So if different surface conditions did not influence speed-related crashes, we would expect each pair of bars to be equal, as is the case with the wet surface condition. This is not the case, however, as the icy surface road condition pulls up the percentage of speed-related crashes. That is 6% of all crashes are occurring on icy surface conditions, and almost 16% of speed-related crashes occur on when it's icy. Therefore, speed-related crashes are overrepresented by icy surface conditions, here and then there.
Did these conditions come solely from the official accident reports, or how did that
Correct. The database was given to us. We didn't have any flexibility in that. You know, each characteristic, so surface conditions had, there was a couple other variables that we omitted just because they were so non-essential to the analysis. They had such a minimal amount. But yeah, we just had to work with what was there.
Do you know if they take measures to increase objectivity in those reports? Do you know to what extent subjectivity is an issue?
It is very it's a subjective report. The officers are, I'm sure, instructed to, just analyze the situation that they come upon and fill out the report. It's, I don't think there's a whole lot of leeway. They either check a box or not. And that's also an issue when it comes to speed, which is the focus of this topic, is that on that report, was speed involved, yes or no? So that's definitely something to keep in mind. I don't know the level of objectivity that the officers are asked to maintain. Is there another question?
Yeah, did you also look into whether most of these happened in the daytime or at nighttime, the accidents, visibility-wise?
Whether or not the factor there was daylight conditions, whether or not it was sunny, or whether there was daylight, nighttime, dawn, or dusk. And we did look at those using a similar technique right here, and they just turned out not to be a significant factor for our purposes.
One more. Were these all on all roads, or just 2-lane highways or 4-lane highways? Or
it's all roads in the DOT, the DOT file. Oh, actually, yeah, it's all highway, state-listed highways. So there was a variable for how many lanes. So as I was getting at, we used this method on each crash characteristic in the field variables that I mentioned earlier, and found that ice and curves to be the two variables where speed-related crashes were overrepresented. So this map shows the critical locations of speed-related crashes on icy surfaces. And these two sites, and possibly many of the blue or medium sites on the map, are prime candidates for further study and possible implementation of a ITS safety enhancement that addresses icy surface conditions. This is the same map, except instead of ice, we're looking at speed-related crashes that occur along curves. And again, as with the previous map, these three critical locations and possibly some of the medium locations are candidates for further study. Yes, sir?
Process for segregating between, the low, medium, high. I mean, how was the decision made that 1 through 3 would be low and 13 through 27 is high?
We went through using the GIS software. We just sort of picked different bins. We tried this and tried that, and we tried quartiles, and sometimes it was pretty intuitive, like, obviously we're just going to do this because there's a huge gap somewhere. So it was more or less just as some way to divide it, to sort of segregate the data for visual purposes as a tool to display. Didn't necessarily have a scientific formula that we used. Okay, so we're getting at this methodology here, which is the main purpose of these maps. You can see that it could be a useful tool for decision makers in highway safety world as they seek to best use their limited resources to improve the highway safety. One thing to keep in mind is that some of these critical locations may stick out in the year 2001, possibly because of road construction or a freak ice storm. But they may not stick out over a 3, 4, or 5-year period. Therefore, our next step with the study would be to incorporate additional years of crash database to strengthen the analysis. One other thing to keep in mind is the location that is being highlighted in southwestern Oregon right now. As it is highly significant to the second half of this presentation. We will move now from this macroscopic look at highway safety in Oregon to a much more microscopic analysis of that little purple circle. For the rest of the presentation, I will focus on the second aspect of my highway safety research. which involves the safety countermeasures that address speed-related crashes on curves. So welcome to the evaluation of the Myrtle Creek Advanced Curve Warning System. The location was identified as a problem area because of very sharp curves in the highway, as well as the presence of excessive speeds. The combination of those two aspects led to a high crash frequency rate, which is 5 times the state average. In April 2004, Oregon Department of Transportation installed a pair of changeable message signs to address this problem location. The system uses a radar to display the speeds of the fastest car that it detects in the radar cone. And then it uses the changeable message sign to display a warning message appropriate to vehicle speed. Portland State University was asked to conduct an evaluation of the before and after effects of the system. And this has turned into a classic before and after study of the effectiveness of the sign to reduce speeds, and eventually, in the long run, to the effectiveness to reduce crash frequency. It is worthwhile to take a closer look at the crash history of the Myrtle Creek Curves area. As I mentioned a moment ago, the crash rate is much higher than the statewide average. Between 1998 and 2002, the crash rate at Myrtle Creek was 1.18 crashes per million vehicles miles traveled. And this is compared to a statewide average of 0.22 crashes per million vehicle miles traveled. Additionally, there were 33 reported crashes on the curves during that 5-year period, and 13 occurred on the sharper or southbound curves, while 20 crashes occurred on the northbound curve. In total, there were 12 injuries, 3 of which had serious injuries, and there were no fatalities during that 5-year crash analysis. 70% of the crashes that I'm mentioning occurred with just one vehicle. And then finally, there were significantly more truck crashes in the southbound curves. And in fact, 11 of the 13 of those crashes were truck rollovers. And this serves to highlight the fact that these are very, very sharp curves, especially in the southbound direction. The Myrtle Creek Advanced Curve Warning System is not in a league of its own. There are numerous examples of similar ITS systems being used to enhance highway safety. Truck rollover warning systems are used in varying applications to warn truck drivers of an approaching dangerous curve. In Northern California, on Interstate 5, there's a series of dangerous curves, and so Cal DOT installed 5 changeable message signs with radar guns that operate similarly to the Myrtle Creek system. Texas has used curve warning systems on some of their particularly dangerous freeway off-ramps, as well as Virginia and Maryland. The systems in both Maryland and Virginia are a little bit more high-tech, as they involve what's called a weigh-in-motion system, and it detects the weight of the vehicle and also can detect the speed and the height to better convey safety warning messages. And the more external information about the environment that a system can collect, the better capable it is at portraying a message at the correct time. So then we also have downhill truck warning systems. And on I-70 in Colorado, a downhill truck speed warning system determines the weight of semis as they pass through that system, the weigh-in motion device, and then a changeable message sign calculates it and displays a safe speed for drivers to travel down the hill. And then there's also a downhill warning system in eastern Oregon, and that's on Interstate 84, just northwest of La Grande. This system is similar to the one that I just explained in Colorado, with one nice additional feature. Semi-truck companies can actually subscribe to a service and have an identification box in their trucks. When their trucks go through this system, the system recognizes that truck and actually displays the company name of that truck on the warning message. And the idea being conveyed here is that the more personalized a warning message is, the more effective it is, because that person says, oh, they're talking to me. It's not just a generic message, and generic warning signs tend to be ignored over time. So staying in Oregon now, we'll move back to the Myrtle Creek project. Here you can see the location in southwestern Oregon. It's on Interstate 5 at marker point 108 near the town of Myrtle Creek. This is about a 3-hour drive from Portland. Geographic constraints of this site necessitate the sharp the sharp curves, because it's following the South Umpqua River and it's going around a mountainous area. This photo should give you an idea of what we're dealing with here. Fairly sharp curve. And you can see the river a little bit off to the right there. I also labeled the changeable message signs for both northbound and southbound to sort of give you a bird's eye perspective of what the drivers might be approaching at and looking at. So, yes?
Does that curve that you had there, does that meet current AASHTO requirements, or is it especially sharp?
As far as I know, it does. Actually, documents here in the back probably can give a verification on that. Sorry to put you on the spot.
With the radius. So.
Okay. So the changeable message signs were installed for both northbound and southbound travel directions. The signs were installed on existing sign bridges, and using that existing infrastructure saved literally thousands of dollars in the total cost of this project. A radar unit for speed measurement was installed on a pole near the sign bridge at a height of about 20 feet, as seen in that photo. The radar uses Doppler technology to detect both vehicle speeds and travel direction. Due to the layout of the highway and the lane geometry, the ability to detect travel direction was important to filter out vehicles that it detects traveling in the opposite direction. The radar was initially set to detect the strongest signal, which was oriented for semi-trucks, but after testing, ODOT decided to switch that to detect the fastest vehicle being picked up. The entire Myrtle Creek Advanced Curve Warning System cost $140,000, and again, that represents a huge savings because of the existing infrastructure. To sort of put that in terms of a cost-benefit analysis, in 2002, the 5 truck crashes that occurred up until that point, the previous 5 truck crashes, cost $176,000 in total costs. And that's including delay time, cleanup costs, lost goods, and that's just the southbound. Northbound, it was $25,000, so less than $200,000. We're looking at $200,000 total cost of 5 crashes, $140,000 for the system. After we do the crash analysis, the long-term crash analysis, you'd be able to sort of put a cost benefit and determine whether or not this was a cost-effective device at saving money. Yeah.
Is that cost just for the public, or is that private cost as well, like for the trucks?
The information that I have here says lane closures, delay time, and lost goods. So, yeah. Okay. So here we take a look at the actual changeable message signs messages. There are 3 messages: a default message, a warning message, and an excessive speed message. You can see that each message correlates with a different speed range. The default message is good for speeds less than 50 miles per hour, and there are 2 panels that are displayed. The first panel in the default will say caution. The second panel will say sharp curves ahead. If the radar detects a car between 50 and 70 miles per hour, the first panel will say slow down. The second panel will say your speed is 57 miles per hour, or whatever the speed the fastest speed being detected is. If the fastest speed being detected is greater than 70 miles per hour or greater, then it will display the excessive speed message, which says slow down, your speed is over 70 miles per hour. And it tops out at 70 miles per hour, basically to prevent daredevils from throughout the West to seeing how fast they can get clocked going through these dangerous curves. Here we have our northbound before and after photos. You can see the sign bridge was there, and the previous warning was flashing blinkers, suggested 45 mile per hour limit. And then here's the southbound photos, dealing with the same type of thing. So the objectives of the study. There are 3 main objectives. The first is the before and after analysis of the crash frequency. But like I said, we need to wait 3 to 5 years to really get a good idea of how this is affecting crashes. So we'll wait. And hopefully I'll be done with this program and somebody else will be giving that presentation. Compared to other locations of similar, what we need to do then is compare that before and after crash analysis with similar locations with similar geometry that did not receive assigned treatment. That may be fairly difficult with this study just because of the uniqueness of the Myrtle Creek curves. But yes, sir?
Is it possible to add a photo radar camera that issues citations for excessive speed and see how the compliance changes?
Yep, it is possible. I would imagine it's possible just because of those exist in the city in certain locations. However, from my understanding, ODOT has made clear that this is not to be intended to be used for enforcement, for traffic enforcement. Yes.
Well, and I realize that the 45 mile an hour is the yellow advisory speed. What is the actual speed limit on that section of road?
50 miles per hour. Yeah. So the second objective is the before and after analysis of the speed data, and this was sort of the heart of the project. Had a lot of hands-on data collection and data analysis that I was a part of, and I'll explain that more in a moment. The third objective is to evaluate driver awareness of a sign with a survey that we conducted during post-installation data collection days. And we did those surveys at northbound and southbound rest areas. So the measures of effectiveness, how we sort of analyze the study, is to look at the change in the mean speeds of both passenger and commercial vehicles, and then the change in the distribution of those speeds also for both passenger and commercial vehicles. And then for the survey, our measure of effectiveness is to just evaluate the public responses to the sign, and we did that by directing certain questions about whether or not they saw it, whether or not they thought it was a useful tool. The speed data collection, went down for 4 days before the signs were installed, October, November, and December of 2003, and then for 3 days post-installation. The signs were installed beginning of April. We went down shortly after that in May and in June again. And then we used an ultralight laser speed detector when we were doing the field collections. The laser gun was hooked up to a handheld computer, and basically if I'm holding the gun, I would point it upstream, zone in on a car, hit that car, and then whether or not, let's say it's a car, I would hit an appropriate button on the handheld computer, and then the system knows that we're dealing with a passenger car. Then I would follow that car as it approaches me and goes through the curve. And then I would just hit reset, go back to the start. And if I hit a semi-truck that time, I would hit the appropriate button. And so the data collection, sort of we pre-filtered passenger cars versus commercial vehicles so we could better understand how those different drivers were responding to this treatment. All right. This sort of tells you the location of where we collected the data. The blue stars represent where we were at on the curves. In the southbound collection, we collected the data from a vehicle that was in the ramp Gore, the exit ramp to going into Myrtle Creek, the town. And then in the northbound, we collected data from behind a concrete barrier that was about 420 feet downstream from the actual changeable message sign. And each time that we went down there and collected data, we tried to minimize the variability so that the driver responses would be similar before and after. So we didn't want to be waving a big red flag afterwards because that would spook people out and cause, as an example. So we minimized that variability for analysis purposes. When we analyzed the data, the first thing we did was a cosine correction, and that's due to the angle. Because we're not pointing directly at a vehicle, we're sort of set back 30 to 50 feet. The speed detection needs to be cosine corrected to get an accurate analysis. We did not, however, correct for the road geometry, because looking at that, it seemed to be a pretty minimal factor. Then, as I've been saying, we've divided the data into passenger and commercial vehicles and split the vehicles into, or the speeds into different bins or zones. And we use 200-foot bins starting at the location of the sign. So from the sign to 200 feet upstream is one bin, and then from 200 to 400 feet is another bin. And we looked at speed, we looked at our statistics of the speed analysis for each of those bins to see where along the curve changes might be occurring. And this will all become pretty clear once I show you the charts. The main tools that we used to compare the before and after speeds were your basic statistics. We used the mean, standard deviation, and 95% confidence intervals to tell us whether or not changes were occurring in the speeds. So the results, the moment we've all been waiting for. Here we're taking a look at the southbound chart. The blue diamonds are the before speeds, and the pink squares are the after speeds, the mean speeds. The sign is the black vertical bar at 0, just right of center. The sign becomes visible at the vertical dash at about negative 400 feet from the sign, 400 feet upstream from the sign. And then the light gray dashed lines, vertical dashed lines, represent the speed bins. Those are every 200 feet. So we took the means, and then the whiskers, coming up and down from the diamonds and the squares, represent the confidence intervals, the 95% confidence intervals. Yes, Peter?
Yeah, what was your sample size for both the before and after?
Quite large. I don't remember those numbers off the top of my head. We had between 200 and 800, depending on whether or not it was passenger or commercial, before or after. We're dealing with a bunch of different ones, but I don't remember those exact numbers off the top of my head. Sorry. So basically using the confidence intervals as a way to gauge whether or not there's a difference. If the confidence intervals overlap, we cannot say with confidence that there was a change in the mean speed, even if the after or pink is below the blue diamond. However, if the whiskers do not overlap, we can say with 95% confidence that there was a change in the mean speed before and after. So this one works pretty good. To the left, they're far away from the sign. No difference. Absolutely no statistical difference. As they approach, there starts to become a difference. And then as they reach the sign, there's a huge difference, huge relatively, between the before and after speeds. And then that lower speed of a few miles per hour stays lower as they go through the curve. And now that was passenger. Yes, sir?
Yeah, I have a question. At what point would they be able to notice you with the gun along that trail? And how would that have an effect of your before speeds and after speeds?
It would only have an effect, or in theory and ideally, it would only have an effect both before and after, right? So the changes, we minimize that variable by making ourselves seen the same amount before the sign was installed and after the sign was installed. So that sort of controls for the fact that we were present. So they saw us, does that make sense? Okay. But to answer the question a little bit more directly, it depends on whether we're dealing with northbound or southbound. In the northbound travel direction, they saw us much later than they did in the southbound travel direction because of the nature of the geometry of approaching the curves and the fact that we're behind a cement barrier. Whereas in the southbound travel direction, we were in a car right off the side of the road. It was fairly obvious. Yes?
Since the southbound direction, you look like you're a cop car just waiting to pull someone over. Might that explain why your beginning speeds at the start are way lower in southbound than northbound?
Yes, that is a possibility, one that I don't know for sure, but definitely a possibility. There's lots of variables that we couldn't precisely say. There's also an S-curve a mile or a half mile before the curve in the southbound direction. There's also construction half mile before the curve in the northbound direction. But those variables were the same before and after, so they're controlled. So the previous slide was passenger vehicles in the southbound direction. This is commercial vehicles. Very similar story. Not a huge difference or no difference at all before the sign becomes visible. And then once they hit the sign and go into the curve, quite a difference. Yes? Okay. Now we're moving to the northbound. This one's not quite as glamorous of a picture, probably not the one that we'd throw in the textbook. But this is passenger vehicles. The reason why there's such variation in the negative 700 bin is because that was a really difficult location to hit with the laser gun. So we had very few speed data collection that far away. There was a tree, and it was coming around a curve. So, that's sort of an anomaly. But as you can see, once they hit the sign, go into the curve, and throughout most of the curve, there is a statistical difference in speeds. And then with commercial vehicles, again, not quite as glamorous as a picture. The negative 700 after, that was only a couple commercial vehicles, so that's not too valid of a data point. And then going into the curve and throughout the curve, there's no difference here. That's all right. As I mentioned, one of the other measures of effectiveness was the speed distributions. And for simplicity, I'm just showing the one chart here. But blue is before speed distribution. Pink is after the sign was installed, speed distribution. So you can see that the blue bars tend to be higher in the higher speed categories, and the pink bars are after tend to have a higher percentage in the lower. So that represents a shift, a downward shift in the distribution of speeds, which is good. And then the survey results. We did these surveys at the nearest rest area in both directions, which happened to be 35 miles north of the site and 26 miles south of the site. And went out there for all three of the post-installation data collection days, went up to people and asked them if they'd take a survey. Fairly interesting experience. But we did get 87 surveys collected total. And for the most part, passenger vehicles, for the most part, they noticed the sign. And for the most part, they saw their speed or thought that it displayed useful information. One of the things that we were particularly interested in is if they thought it was in a good location, and if the visibility, size of the letters, reflection of the sun, if all that was good. And we're pleased that most people thought everything was doing good. So the conclusions here are that there is a reduction of speeds for the majority of vehicles in both directions. Tended to be closer to 3 miles per hour in the southbound direction and lower, around 2 miles per hour in the northbound travel direction. And also, public response to the device was positive. Did I see a question?
Yeah.
Do you think your results might have been different if you used displacement tubes instead of a laser gun?
Yeah, it's possible. Again, I keep defaulting to this, but we controlled for that just because we were the same before and after. But I think it would possibly be different in that all the speeds before and after might be a little bit higher, just because the displacement tubes wouldn't be as noticeable. But I think the results would more or less say the same thing. One thing you can do, you can basically do this, the Cadillac version or the basic version, and my guess is that it would be the same results. The results might be stronger or more scientifically sound if you spend a lot more money and use higher tech equipment and spend more time doing it. But I would guess that you're still going to say that speeds reduced about 3 miles per hour southbound and about 2 miles per hour northbound. And then the last measure of effectiveness for the motor vehicle crashes, we just need to wait and then hear from somebody else. So I want to thank you all for coming. I also would like to thank Dr. Bertini and Dr. Mansier. You guys have given me a lot of guidance throughout the year on this project. People at ODOT that helped me out, Matt Lasky, Steve Hansen, Dr. Kimple here at the university that helped me out. And that is it. Thank you very much. Dr. Bertini?
I have an email question for you.
Yes.
Do you think there is any differential application and efficacy of the treatment to other features than curves like straightaways, downhill, uphills, or crests that are prone to ice problems?
Say the first part again. Differential treatment? Could it work somewhere else? Yes, it could. And this was sort of a pilot program. One of the reasons why Myrtle Creek was selected wasn't necessarily because it had the highest crash frequency. It was easily done because of those existing sign bridges. It saved not quite half the cost of the project, but a lot. So it sort of stood up that way. And then the fact that it had 5 times the crash frequency obviously was a big one. heavily traveled area, so it was just a real easy test pilot to see whether or not these type of projects are really worthwhile. So the first part of our analysis is saying that yes, here in Myrtle Creek, it's working. We'd still like to see crash data after a while. With respect to ice, that's one of the things that we're looking at with the first half of this research that I was talking about, determining where speed-related crashes are occurring, mapping out those ice spots. The next step there, after incorporating more years' crash databases, is to go out and look at those sites. What's actually happening here? Is there something else besides ice that is making those crashes happen? Maybe it's happening a lot when it's icy, but there's also no lights there. Or maybe it does just need an ITS sign during snowstorms or ice storms. Yes, I guess the answer is yes to that. Yes, Steve.
You said that 11 of the 13 crashes southbound were commercial vehicle?
Overturned commercial vehicle.
They're overturning. Yeah. Do you have any determining a correlation between the types of loadings those trucks had, or did you have access to that data?
I have not looked at that at all. The type of loading. I would guess that you could dig in and get that type of information. I'm sure in the crash databases, if somebody wanted to sponsor you to spend the time to do that, it's probably possible. In the back.
Just a quick question. What was the time between your before and after study? Was it a full year to the day of the week?
Not quite. I went down October, November, and December, so the fall and winter of 2003, basically the fall. And we had collected enough before analysis, had a downtime of a few months. The signs were installed, one the last week of March, and then the other one the first week of April. So basically, April 1st, the signs were installed, and then almost immediately we went down, like a few weeks after, middle or end of April, we went down for our first post-treatment data collection. And then, so in total, you're looking at about 6 or 7 months, 3-month gap in between or so, 2-month gap in between. Yes?
You showed some maps earlier. It looked like, the curve-related accidents were pretty evenly distributed throughout the state, and all of the ice-related accidents were all in the Cascades or on the east side.
Yeah.
So do you think, this system will work, in conditions which are really more weather-related, not necessarily speed-related?
Yeah. I didn't go into the intricacies of weather-relaed ITS systems. My research focused on the curve ones. That's obviously what I'm more familiar with and wanted to talk about. But there are similar ITS systems that can address icy conditions. They can be linked up to weather service systems so that when snow or ice starts to fall, it can activate a system to alert drivers that there may be ice on the road. Is that?
Yeah, that answered my question, but ice-related conditions are pretty widespread, and I think, they're not like curves, so.
Right, and I guess that sort of highlights the importance of this just sort of being a first step and trying to look at those spots a little bit more to see if it would be appropriate. Yes, Dr. Bertini?
More of a comment that is not maybe more for the group, but I was in Japan last week meeting with a European delegation of officials related to highway safety and talking about other countries' strategies toward improving highway safety. And in France, for example, the French president said that their number of fatalities is unacceptable to him on the highway system, so he basically said that they're going to cut the number of fatalities in half in that nation. And one of the things that they did is they changed the Constitution to allow automated enforcement of speed on the federal highways in France. And so they're deploying 1,000 speed cameras, obviously at 1,000 locations on the highway system, and they have up till now implemented, I think, 135 of them. And what they're finding, we also had some auto manufacturers' representatives in this meeting, and the people from Renault were saying, for example, that people are now demanding that auto companies put speed governors on vehicles so that when you enter a road section and the speed limit is 50, it's kind of like a cruise control, but you set the maximum speed at 50 so that you don't get a ticket. And I think they've sent out over 1 million tickets, speeding tickets. And again, to me, it's too early to tell what the impact has been, but they said that they have seen a 20 to 25% decrease in fatalities already. So maybe we could, since we have a few minutes, you could comment on that, and others could comment on whether you think Oregonians or Americans would accept similar enforcement strategies on the highways.
That's pretty interesting. I think that we're probably a little ways away from that for a lot of reasons. Yeah, I'm just going to stay with that. Did you have a comment on that, Aaron?
Just to follow up on that, I've actually driven on the French auto route system quite a bit, and I noticed that change more recently. In a lot of places, similar to the system that you were showing earlier, it displays your license plate. So just from my personal experience, I found it to be very effective for obvious reasons. But I did notice quite a few other drivers. I did notice that was very effective just in terms of simple observation. The extent to which it was personalized as opposed to just seeing a flashing light or slow down. That actually displayed the license plate. It obviously had a much greater effect.
And in Portland, we have that capability. One of our fellow students, Matt Lasky, has been working on a license plate reading system, but it also has been very explicitly stated not to be used for enforcement, but simply to measure travel time. So the technology certainly exists. It's just not widespread here. I think the opposition, as far as rights of the freedom and control of what those imply, would be fairly difficult at this point in our time. Yes?
Yeah, I'm from Southern California, and I know that the outrage there was quite louder before it was actually implemented. And after they started doing it, it seemed to calm down. People were getting tickets, but they can't continue doing it, and nothing stopped them, so they might just do it anyway.
Yeah, and I guess, like in the case of France, 25% reduction in fatalities, is that what the sort of the preliminary? You start to see numbers like that, and it's hard to argue against it, no matter where you're at in our country, I would imagine.
Just continuing to comment on that, I'd like to say that personally, as an American and an Oregonian, I would not be willing to accept such a system as France has implemented. So, that's my personal opinion on it, though.
And you're not alone, I'm sure. Lance?
One of the figures that really jumped out at me in your presentation was the average speed. Even now, after all the implementation, it looks like roughly 50% of the traffic is still going over the speed limit.
Right.
And I'm sure if you did this or did a similar project in other places on I-5, you'd find that 80 or 90% of the people were going over the speed limit, and not just by 5 or 7 miles an hour, but by 10 or 20 miles per hour. And yeah, I mean, systems like this are a bit of an invasion of privacy, but at what point are we going to put our foot down and enforce the speed limit?
Right. Is that a question or a thought? I mean, I agree with.
It's a thought.
I completely agree.
But I guess my question is: did the mile per hour difference, did it surprise you that it was only like a 3 mile an hour reduction?
I really was not sure what to expect. Some of the other studies, when I was doing the lit review, ranged from minimal 1-2 miles per hour to 7 or 8 miles per hour. But I think it's just so site dependent on what other variables go into the geometry or the initial speed or what type of implementation is used. I wasn't sure what to expect.
I don't know if I missed this, but do you have preliminary results on the change in accident history?
I do not have preliminary results. Talked to Ed Anderson, who's the lead engineer on this project at ODOT. He said since the signs have been installed, so far there's been one minor accident. It was not a rollover. That's all I know so far. Well, I think we're right at our time. Are there any more comments or questions? All right.
Before we thank our speaker, we want to thank Casey very much, and I'll remind you that next week, Dave Cox, who's the administrator of the Oregon Division of the Federal Highway Administration, someone in this room's boss, I think. He will be here talking about the FHWA view of transportation in Oregon, so I encourage you all to attend next week as well. And let's give Casey a big round of applause.
Thank you.